So in this third installment on quality management, we'll focus on statistical process control. So this is where you get a chance to remember some of the statistics that you did in your earlier course. All right, so we'll bring it to bear. So what is statistical process control and why is it important? Well, particularly in manufacturing environments, also we could apply the concept in service environments, but let's think about manufacturing environments for a moment. A process is used to produce some form of output, and that output usually has some specifications. If we could produce that output according to the specifications in a consistent manner, without any major extreme values, we could say that that process is stable. What if we wanted to determine if the process was not stable? And when we say not stable, it means that either the average of the process is changing or the amount of variation in the process is changing. And the reason why we want to know that is because if your average is changing or your variability is changing, there is a risk of producing defective items. And so as a result, you want to make sure that your process is in control. Similarly, in a service environment, if we want to be consistent, we have to ensure that the process that we're using can deliver whatever that service is and whatever metrics where we use to measure the service, the performance of that service. We have to be able to show that we are consistent in meeting that particular service standard. So for example, if you're going to open a bank account and it's supposed to take you 30 minutes to open a bank account, every time we open a bank account, let's say a similar one, either checking or savings, that we are supposed to get a time that is within a set of acceptable limits. And what if it took 2 hours to open an account? We'll say, whoa, this is definitely not consistent. What if we notice that the time that it takes to open an account is increasing over time? We'll say that this process is not stable. So we have to look for the reason for that and correct it. But statistics could actually help us do that. Because if you recall, those of you who have done statistics, if you recall hypothesis testing, essentially determining if a process is stable is really a hypothesis test. We would look at the output from the process, and if we get values for samples that fall outside of the acceptable range, which is usually plus or minus 3 standard deviations from the mean, values that fall outside of that, we call them outliers. And outliers are indications that our process is out of control. So in other words, we will reject the null hypothesis that says the process is in control, and we have evidence to the contrary that the process is out of control. What do we do with that information? We pause the process and then we try to find the root cause of the problem. So let's explore this idea a bit more, okay? So we want to explain the purpose of a control chart, and the control chart is really the upper and lower limits of what we call the acceptance region, and outside of those limits is what we would call in hypothesis testing the rejection region. Explore the role of the central limit theorem in SPC, which is statistical process control. Build X charts and R charts, and list 5 steps involved in building control charts. All right. So we want to learn a bit about P charts and C charts as well. So in the first case, the R chart and the X chart, those are charts for what we call variables. Variables are things that we measure, like time, volume, okay? But then when we accounting, like how many blue shirts, red shirts, how many defectives, and so on, then we refer to those as attributes. And so we use different charts for those. We use a P chart and a C chart. Okay, so let's get into some of those. We will learn a little bit about the idea of process capability and compute what we call the process capability, or the left side capability and the right side capability. We're not going to do acceptance sampling in this course, right? We're not going to cover that. So a process is used to monitor standards by taking measurements and corrective action as a product or service is being produced. And then what we're doing is we're applying statistical theory to that process to determine if it's in control or it's not in control. As I've already mentioned, it's just a hypothesis test. Excuse me. So variability is inherent in every process. If we go back to the example of opening the bank account, I'm sure you'll agree that every person who comes to open a savings account is not going to experience exactly the same amount of time. It'll be approximately the same amount of time if it is a 30-minute transaction or 40-minute transaction or whatever it is, but approximately the times will be the same for different customers. If there's a customer that has a unique situation, then you expect that to take a bit longer or maybe even shorter. And if that's the case, if that value in terms of the amount of time falls outside of the normal range, then we have to say there's an assignable cause. There's a reason for that. But if the values just fall within the range of what's expected, maybe 35 to 45 minutes, then we refer to those as common causes. Common causes because a customer will experience the same set of conditions. But the special causes or the assignable causes are what we want to identify. Okay? So an example of a customer service representative taking 2 hours to open an account might be because maybe the computers were shut down. There was a problem. The customer didn't have a particular piece of information. They were trying to retrieve it electronically. Or that the customer service representative is a new employee who made some mistakes that had to be corrected. I mean, there could be all sorts of reasons. All right? So statistical process control provides statistical signal when assignable causes are present. And that's when you have these outliers that we're talking about. Detect and eliminate assignable causes of variation is what it allows us to be able to do. Natural variations, however, are called common causes. Affect virtually all production processes. There's an expected amount of variation, and output measures follow probability distribution, whether or not it's a normal distribution or some other kind of distribution. And for any distribution, there is a measure of central tendency and dispersion. If the distribution of the output falls within acceptable limits, the process is said to be in control. But if that distribution falls outside of the acceptable limits, then we say the process is not stable. All right? So, assignable variations, so-called special causes, generally this is from some kind of change in the process, and then you could actually trace them and find out the root cause. The objective is to discover those when they are present, and then to undertake appropriate action to get rid of them. Right? Now, to be able to do that, we have to take samples. We have to take, so if you, let's go back to the banking example. We will take samples of 5 customers at a time. So one sample, because remember that when we were dealing with hypothesis testing and so on, we had, it actually was connected to sampling distributions. So what we do is we will decide a sample size, let's say, for example, 10 customers, and we will sort of like monitor 10 customers and take the average times. The next 10 customers, take the average times. The next 10 customers, take the average times. And so each of those blocks of 10 customers or groups of 10 customers represents a sample. And that sample will give us a sample mean, an X bar, and a sample standard deviation, SI. All right? Now, if we take M samples, then we could calculate X double bar, which is the average of all of the samples. I equal to 1 to M. And we could even calculate S, which is the average, S bar, S bar, which is essentially the average of all of the sample standard deviations. Let me just remove that. All right, over M is equal to 1 to M. So technically speaking, we could get the mean and standard deviation, all right, of the process. Now this S bar, or we could call it this S bar, sorry, will be the estimate of the standard deviation for each sample mean. All right. So the sample not the sample mean, but for each sample. And if we take the average of those, it then becomes an average, if you wish. If we take an average of those, it becomes an estimate of the true population standard deviation sigma. And we could actually use that later on in finding what we call these control limits, which are like confidence intervals. Okay? But there's a special way that we approach that, and as we go through this lecture, I will sort of show you that. So we take essentially samples. Say, for example, 5 boxes of cereal taken off a filling machine, vary from each other in weight. Enough samples are taken to form a stable process, and they form what we call a distribution. So to measure the process, we take samples, analyze the statistics as follows. So then there are many types of distributions, including the normal, which is the bell-shaped curve. But distributions do differ in terms of central tendency, that is the mean, and the standard deviation, which is the variance, and the shape of them. Sometimes it can be slightly skewed, etc. So if only natural causes are present, then of course the process distribution should be within the limits, as if only natural causes. What do we mean by that? It means that if these are your specs, then if only natural causes are present, then the distribution should be within the limits. But if you have assignable causes, then these are outside the limits right here. And that's where you have your defective items, all right? So that's your limits for your process right here. So assignable causes are here, but common causes are in this case, and we have nothing falling outside of the limits. If assignable causes are present, the process output is not stable over time, and it is not predictable, which makes sense, right? So this is just showing you that samples could have different shapes and so forth. And then if the process is stable, that means the mean, all these samples that you take, the mean and the standard deviations are more or less the same, then you'll be able to predict what you can expect to happen. But if you have variations, as you can see, we started here, but look at that, the variation has changed in this one. Not only that, if we look, the center mark is not passing through the center of this distribution, right? Look at the center here as well, is away from this one, and look at the width of it. The variation has gotten much larger. So as a result, it is hard to predict what will happen next because this process is not stable. All right, so by plotting data, we actually can gain some insight into whether or not a process is stable. All right. So we actually construct these control charts from historical data, and really they help us distinguish the assignable causes from the common causes. Let's look at this in this case here, where the dotted line represents the the specifications upper and lower limits for a spec. As you can see here, these appear to be in control, right? Now, if you look here, it looks like the center line is going through those. They appear to be sort of stable with respect to the mean, but clearly they have parts of them falling outside of the limits, in which case the process might very well be stable, statistically stable, but it is not capable because this is falling outside of the range that is acceptable. And so therefore you're producing defective items even though your process is actually stable. And this is one where you notice that not only we have variation in the shape of the distributions, we have also variations in terms of where the means are, right? So as a result, this is definitely out of control, and you want to be able to detect those as much as possible. Now, the kind of control charts that we generate, so charts will help us determine that. And what those charts are essentially confidence intervals. Remember, confidence interval, when we did those, will contain the data, right? Sample means or sample proportions, etc., will contain the data with a certain probability. So, well, I shouldn't say the data. Well, certainly the bucket of data will fall within there. But what happened is that it also helps us estimate where the population, either parameters, which is the mean or the proportion, and so on. All right. So those control charts or confidence intervals, sorry, help us to be able to assess that. Well, it's much the same way here, is that when we develop these control limits, they're essentially confidence intervals, and we're saying that the parameter that we're interested in, which is like the mean of the process, should be in there. So if there are values that fall outside of the range, then we're saying it's possible for the process mean to actually fall outside, in which case that process would not be in control. All right? Cool. Now, in terms of the kind of charts we use, will depend on the kind of data that we have. We have two main types of data: variables, and then these are usually things that we can measure, characteristics that can take any real value, maybe in whole or fractional numbers, and we can express it using continuous random variables. So weight, time, right, volume, etc. Anything that we measure, we will consider a variable. So we can measure those, and then we, let's see here, just trying to find a different, and then here we count. So defect-related characteristics, classify the products as either good or bad, categorical in nature, they're discrete. So because they're discrete, we could actually count them. So that's why we could actually get proportions, the proportion of defectives and so on. So interestingly enough, we're coming back to the central limit theorem, which is a theorem that says that regardless of what the population distribution is like, if we take sample sizes that are sufficiently large, eventually the distribution, or if we take, the distribution becomes approximately normal. So it doesn't matter if we have a distribution that's slightly off center like this. If we take samples from it, enough samples, then As the sample size gets larger, the actual distribution will become approximately normal. And this mean will be the same as the mean of the population, right? So we'll have the same population mean mu, but the standard deviation will be the population of the standard deviation divided by the square root of the sample size. So this is just taking you back to your statistics course. All right. So what we're saying is that no matter what your distribution looks like, you could actually end up with this for the central limit theorem, as long as your sample sizes are sufficiently large. And some of you may remember we used to say when the sample sizes exceed 30, we consider them large enough. All right. So let's get to the control charts for variables. All right. We have continuous dimensions such as weight, speed, length, strength, and all those sorts of things as we talked about. And an X-bar chart is one of the charts that we use to monitor the process mean, an X-bar chart. And then we use an R chart to measure or control the spread. So we use that to control the spread of the data. All right. So variables are things that we measure, example, weight, speed, length, strength, etc. And then we could get an X-bar chart and an R chart, where the X-bar chart helps us control the mean, and the R chart helps us to control the spread or the dispersion or the standard deviation. And we generally use those two together. All right. So ideally, if we have the population standard deviation, this is what it will look like, right? X bar, you may remember from confidence intervals, X bar some minus, right? Z, which is our critical, sigma over root n, or in other words, sigma X bar. This is the same as sigma X bar, right? But we express it this way. What happens when we don't have the population standard deviation, which in most cases we don't have? We will need an estimate for that. All right. So we could actually use this when we don't know sigma. We will actually look at the range of the samples that we have, the ranges, and using the average of the ranges of each sample, what we will do is then estimate that 3 sigma X bar. That's what that is. That's really just an estimate of it. So A2 R bar is estimating 3 sigma X bar for us, right? And so essentially what would happen is that, let's say these are samples. If we collected samples, the range is just the min minus the max. So for sample 1, we would have max minus min 1. That would give us R1. Max 2 minus min 2 will give us R2. Max 3 minus min 3 will give us R3. All right? So if we now take R1 plus R2 plus R3 over 3, we get R bar. There we go. So that's where we get that R bar from. Okay? We would need to know what the sample size is for each of those, of course. And then each of those samples will have an average. In other words, if for example our sample size was say 10, then we would take the 10 items from this sample 1, sample 2, sample 3. We would take the 10 items from each one of them and calculate the mean. And that would give us our X bar 1, X bar 2, X bar 3. And the X double bar would simply be so in that case, we would get an X bar 1 plus X bar 2 plus X bar 3. since we only have 3 samples, but within each sample we have 10 observations. So we add those up and we will divide by 3. That will give us our X double bar. So using this X double bar and this R bar, we could actually get a X bar chart and a range chart. So we will talk about that shortly. Okay. So here's one example where samples are collected. In this case, 12 samples are collected, as you could see. 12 samples. But each of the samples have a sample size N of 9. So to get our X double bar, what we would end up doing is we would take each of these samples, add them up, sample means that is, these are sample averages, add them up and divide by 12. So the X double bar that you're seeing, which happens to be 16, will come from the sum of all of the averages of that we have here, X bar I over 12. The 12 samples that we have, right? And then we would have to get the R bar, we'll have to get the sum of all the RIs over 12 as well, and that will give us that. But notice that in this example we are using this 1 over 3 or 1 over root 9, which suggests that we have some information somewhere that the population standard deviation is 1. That's the only reason why we'll be doing that. So that means that sigma X bar is sigma over the square root of N. Sigma is 1, N was 9, so 1 over the square root of 9 is what we have here as the sigma X bar. Free standard deviations, and then if we take X bar, which is 16 plus or minus, then we get the limits of 15 grams to 17 grams. What this is telling us is that we expect, right? We expect the process, whatever that process is, we expect if we were to take free sigma limit. So this is the mean 16, and here we will go to 17 and we go to 15. All right. So it means that anything that falls outside of that 17, outside of the 15, would be a defective item or out of control. Right? We're not going to call it defective item, sorry. This is for P charts when we do that. So here would be out of control. Out of control. Okay? So that's the basic principle behind this for sure. And so for the data that we have, did we have anything that fell below 15? Let's see. We have a couple of them. Those fell below 15. And then, well, let's look at what went above 17. We have one went above 17.3. So which means that we have some out of control points. So drawing the diagram, as you could see, the variation between 15, 17, and the average. So these are the control limits right here. If we plot that, we could plot that on graph paper. And this is any variation that takes place within that range will be due to natural causes. Any variation outside of that will be assignable causes. Well, the question is, do we have? Yes, we do. We have 1, 2, and 3 values that fall outside of the range. So as a result, we do have an out of control process. So what must we do? Go and find out what the root cause of those problems are, correct them, and continue taking new samples and until the process is completely in control. Right? So that's what we see here. Here's another example. How do we set control limits? So you're given a process average of 12 liters, an average range of 0.25, and a sample size of 5. So if we use the x double bar plus or minus A2 R bar, that would be for the average chart or the mean chart, then we just be 12 plus or minus A2, and R bar is 0.25. But we need A2. A2 we will get from a table based on a sample size n equal to 5. That table is in, I think, S61, table S61. Let's take a look at it. Here it is right here, table S61. So for a sample size of 5, we will use an A2 factor of 0.577. So if I go back here, I would have to put 12 plus or minus 0.577 times 0.25 will then give us the upper and lower limits for this average chart or the mean chart. All right. Now, for the range chart, we calculate the upper control limit by taking D4R bar and lower control limit by D3R bar. There are two different values, and the same table gives us the value of D4 and D3. So for n equal to 5, D4 would be 2.115, and this would be 0. So the range would be, in this case, we know the lower limit of the range. Let's see this again. 2.115. So this would be 2.115 times R bar, which is 0.25, and the second one would be 0 times 0.25. And that will give us the range chart. And we do exactly the same thing to see whether or not the values for the range are falling within those limits. If they're falling within the limits, it means that process variability is stable. If they're not falling within the limits, then they're not stable. All right. So here we go with, for this particular problem, we have the upper and lower control limits. Here's my upper control limit, which you've already seen that I've shown you that. So upper and lower control limits, 12.144, 11.857. And all we would do is we'll plot those to see what happens. Okay, let's look at the range chart. So in this case, we're still trying to control a process, but for variables, but we are interested in the variation in the process itself. So we want to make sure that we don't have a process that's just going crazy, giving us things like, if this is limits, and that's the midpoint or whatever, you don't want a situation where 1 minute your process looks like this, another minute your process looks like, right? So you look at that compared to this, right? It's very different. Or one that looks like this. So all of these have different variabilities, okay? So in that case, our process may not be in control. So it shows ranges over time, difference between the smallest and largest values in the sample, monitors process variability, and it's independent from the process mean. And that's important to note, that it's possible to have a process which is stable in terms of the mean, but not stable in terms of the variability. Or it's possible to have it sort of stable on the variability, but not on the mean. So you could have both of those, or you could have a combination of them, right? So here's a case where you can see the variability stays the same, but the mean is actually increasing, right? So it does not, the range chart does not detect any changes in the range, but the mean chart is detecting that there is an upward movement of the process mean. And then in this case here, we have the mean is stable, right? But then the R chart is telling you, hey, your variation is increasing, all right? So that's why we have to actually always look at both of those things. So there's some steps in creating a control chart. Take samples from the population and compute the appropriate sample statistic. So either we're computing R bar or we're computing X bar. Use the sample statistic to calculate the control limits. So knowing out our sample size is, all right, we could actually go ahead and calculate what A2 is, D4, and D3. Using that, we could actually get the limits for our control chart. Then if we have any values that fall outside, suggesting that the process is out of control, investigate possible assignable causes and take any appropriate action. Continue sampling from the process and reset the control limits when necessary. That means that after you fix the problem, you shouldn't see the same kind of data. Your process should have been improved, and so therefore you should be able to go back and check your mean and standard deviation, see if there's still cases where the process appeared to be out of control, find those causes and fix them. And then the process is iterative. You keep doing that until your process is truly stable. All right. Now let's think about attributes. Remember we said attributes are parameters that or observations that come from counting. So things like how many good light bulbs are there? You know, how many students said yes to a particular activity versus no? How many of these shipments that we receive are either acceptable or unacceptable, right? So it's usually done by counting. And we could either have two types of charts we're going to consider. There are more, there's lots of charts. But one that's based on the percent defective, and the other one that's counting, and that's based on the number of defectives. This one that's based on the percent defective, you already are familiar with it if you've done statistics. It's based on the binomial distribution. This one is based on the Poisson distribution. All right. So the one that's based on the Poisson distribution, we're just looking at proportions. So we have a sample proportion, we have a sample size n, and our control charts or our control limits would just be p bar plus or minus 3 standard deviations. Where what's the 3 standard? What's that supposed to be? We use our best estimate, p bar. 1 minus p bar over n. All right. So that's just like a confidence interval for proportions. You've seen that before. And then if we have sample proportions that fall outside the range, then certainly we would say the process is not in control. All right. The other one, which has to do with counting of the number of defects, is from what we call a Poisson distribution, where the mean and the standard deviation are very strongly related, because the standard deviation is essentially the square root of the mean. So we usually measure it by C bar, which represents the average number of observations that we're interested in per unit. So when we're counting, it's usually counted per unit. So for example, if we're looking at typos in a document, then the document is the unit. If we're looking at typos on a page, then page is the unit. How many typos do we have? In which case you could collect data from 50 sheets, for example. So your n could be 50. And we're counting. So sheet 1, sheet 2, sheet 3, after sheet 50, you have 2 typos, 1 typo, 0 typos, 5 typos, 2 typos, 1 typo, etc., etc. And then if you average those, you will get C bar. C bar will just be the sum of the observations, right? We call it CI over N. So this is a case where the mean, the variance, I believe it is, or the standard deviation, is it's the same as the mean. C bar. The variance is the same as the mean, so in which case the standard deviation is the square root of the mean. Let me just change this. So the variance, C bar is a sample. So mu is equal to sigma squared. So that's a Poisson distribution. That's the characteristic of it. And therefore, if we are trying to get estimates, when we won't have the population mean, so we'll have C bar as a sample mean. So C bar plus or minus 3 standard deviations. Well, what's the standard deviation? It's the square root of the mean. But in this case, we have to use the sample mean. So it's C bar plus or minus. So that's basically counting the number of defects, number of observations. So it's called a C chart. So that's what we refer to as a C chart. Okay. So here we go with what, as you could see, is how we do this, which that is the standard error. So Z is 3 in this case times the standard error, and that will give us our control chart. And here, population will be a Poisson distribution for C charts, but applying the central limit theorem allows us to assume a normal distribution for the sample statistics. So you see here, that's the mean. The standard deviation is the square root of the mean. And so therefore that gives us these formulas right here. So it's fairly straightforward and relatively easy to apply. So 3 major decisions, or issues, sorry, when we're dealing with control charts. So you have to make some decisions, select the points in the process that need statistical process control. In other words, a process may have many steps. You might decide to control one particular area or the entire process itself. Determine the appropriate charting technique and set clear policies and procedures for managing the performance of that process. All right, so helping you to decide which control chart to use. So when we have variables involved, then we do an X bar chart and an R chart, and then we want to collect samples, 20 to 25 of them. The size is usually 4 to 5, and we could calculate the X bar chart and the range chart. With the P chart, so we have observations are attributes that can be categorized as either good or bad, pass or fail, functional or broken, etc. So it's a binomial variable. That's why we say we can use the binomial distribution, but instead we will use the normal approximation to the binomial. All right. So in this case, you could take samples, 20 samples of n equal to 100. So the idea is that you will look at 100 and determine how many defectives in that sample of 100. All right, and then you will end up with 20 sample proportions. When you go to 1 to 20 over 20, then you get P bar, which is your average of all of your sample proportions. All right, and then we have the C chart. So we are trying to focus on attributes, but we are focused on defects per unit of output. So another example could be, imagine you are bottling beer, and you are looking at the labels on the beer can, and you want to see if there are any errors. In that case, you could look at the number of errors per can, or if you want to do it per case of beer, then you could look at the number of errors per case of beer. Let's talk about the idea of process capability. And when we talk about process capability, what do we mean by that? Well, process capability allows us to determine the extent to which the current process could actually meet the specifications that we have. We can see that by taking a look at this diagram here. So let's just create an example. So let's say this is what our process distribution looks like. This is where I could draw a really nice one there. And that the green lines represent the upper and lower limits of our specification. So that's the upper specification level, that's the upper spec and the lower spec, right? Lower specification level, upper specification level. This has a mean, and if the process is such that this represents 3 standard deviations, this represents the 3 standard deviations. Of course, it's not, it's not accurate, but that's fine. I think we understand it. All right. So as you could see, let's assume that the target for our specs happens to be the same as the mean itself, right? So this is our target right here. So what I will do is I will just bring this down just so that I could draw some lines so that you could see here. So if you look at the, let's just look at the upper level right here. You could see that this distance is larger than 3 sigma. This distance is greater than 3 standard deviations, which means that the process on the right side will be able to, will certainly be able to handle the specifications, right? And then if we look on the left side, looking at the width of what we need to achieve, of the range of, from the target, 3 sigma is smaller than that. So, so therefore that distance is actually also greater than 3 sigma, which means that if we take the lowest, the upper specification limit, and we subtract the lower specification limit, and we divide it by 6 standard deviations, that value will be greater than 1. That's our CP, which is called our process capability. All right? That green doesn't look too cool. I should have used red instead. All right? So CP is just your upper limit minus your lower limit divided by your 6 standard deviations, right? And that should be greater than 1. Now, if that's all well and good, but it is possible for us to get a CP greater than 1, but the process is not capable on one side or the other. So let me show you what I mean. If I took this very same idea right here and drew so we have our X bar, and then we have our, this is 3 standard deviations going up here, 3 sigma, and 3 sigma down there. So the total is 6 sigma. So what if my limits were like this? This is here, and then this is here. The target is probably somewhere around here, in the middle, between the two. So let's just bring that down. All right, that's the target right here. So if we look at the distance between the mean and the upper limit, we will see that that distance is smaller than 3 standard deviations. 3 standard deviations is actually taking us beyond the specification limit. So it means that we are going to have some items here that we actually gone beyond the specs, in which case our process is not fully capable. We can generate defects from it. However, on the left side of it, we are able to stay within the specs. And so I could also change this diagram and say, all right, let me just draw a different one now. And maybe I would draw that one in green. If I were to have something like this. So in this case, as you could see, we will be within the specs, but on the left side, we will actually be out of spec. All right. So in this case, we will produce some defective items right here, but this end is fine. So in other words, one side, on the left side here, in the case of the green diagram, is not within specs. In terms of the black curve right here, it is not within spec. So it means that we could actually measure take a new measure. We're going to call it CPK, which is we're going to measure our process capability this way. Is the minimum, right, of the upper specification limit minus X bar divided by 3 sigma. So we are measuring the distance between X bar, right, and the upper specification limit, and divided by free standard deviations. If that limit is, if that's wider than the free standard deviations, then it has a value greater than 1. And then we take X bar minus the lower specification limit divided by 3 sigma as well. Okay, so if both of those are greater than 1, greater than 1, greater than 1, then CPK would be greater than 1. It means that the process is capable. All right. However, if one of them is less than 1, that becomes your process capability. And in that case, what if this one was less than 1? Then our CPK would be less than 1. Okay, so let's just do an example quickly just to see what that looks like. Let's assume sigma for a process is equal to 8, right? Now let's not go. Okay, 8 X bar is equal to 20. Let's make sigma a little smaller than that. 2. All right. The upper specification limit, let's see here, is 28, and the lower specification limit is equal to 18, right? So given this process right here with the following specs, let's look at CP. Well, CP, we said, was essentially the upper minus the lower specification limit divided by 6 sigma. In that case, it would be 28, right, minus 18 over 6 multiplied by 2, which is 12. So that would be 10 over 12. So as you could see, 10 over 12, this is actually less than 1. So this process is not capable. Let's find CPK. We said it's the upper specification limit, 28, minus the mean, which is 20, over 3 sigma, which is 6 in this case, 3 by 2. Well, let's just write it down, 3 by 2, comma, We have x 18. So lowest x bar, which is 20, sorry, minus the low, which is 18, over 3 multiplied by 2. And we got to take the minimum of those two. So 8 is 8 over 6, so 1 is 8 over 6, comma, and, oops, sorry, 2 over 6, and it's the minimum of that is our CPK. So in that case, it's just 1/3. Our CPK is 1/3. 1 over 3, which is less than 1. So clearly, for this example, the process is not capable. All right? And so that's a very important measure to kind of determine whether or not we need to do something about improving the performance of a process. Okay, so let's just summarize that, and that should bring us to the end of pretty much at the end of our chapter. So a capable process must have a CP of at least 1. It does not look at how well the process is centered in the specification range. Okay, so you see if it is off center, then there's a chance that one of the limits may not be satisfied. Often a target value of CP of 1.33 is used to allow for off-center processes. Six Sigma quality requires a CP of 2. Remember I said to you that you have to reduce the variability by half when you're talking about a Six Sigma sort of program. So in this case here, that's what we'll be looking to do. All right, so here is the formula for CPK. Is the minimum of those two values that we will calculate. All right, and then if the process is not centered, then there's a very good chance that one of those limits are not going to be met. Okay, so interpreting CPK, as you can see here, if it is a negative, then you basically can, the process does not meet your specifications. Because here we could meet that, but we cannot meet it on this side. Okay, all of that is actually out of spec right here. If it is 0, then half of you're basically just meeting half of this. 50% of the time you can meet the specs. It is between 0 and 1, so you're making some progress, but it is not, again, fully capable. And then if it's just equal to 1, it meets the specs, but is very, very tight. And then, of course, if it is greater than 1, then this is what you're kind of aiming towards, right? Somewhere between this and this. Then the process is capable in that case. All right. So we have nowadays with quality management, automated inspection is something that is becoming increasingly used, which then allows for 100% inspection. So you no longer have to now think about just inspecting samples. You could actually use automation to inspect all of your values. So SPC and process variability, as you could see, we talked about the idea that a process could actually be in control, but its variability is such that it could be a non-capable process, right? Sometimes the mean is in control, but the variability is actually out of control. Statistical control is a major statistical tool of quality control. Control charts help to distinguish between natural and assignable causes or variations. There is software to assist in determining the different charts. Yes, definitely. There's software that you could actually use to calculate P chart, S chart, X bar chart, R chart, C charts, and all of those things. There are lots of charts that we're not even touching on. And these charts are tools for evaluation of quality of processes and shipments. All right. So, quality management, as I said, is still extremely important. While there are tools for total quality management, there are tools for statistical process control. Bringing those two things together, both in manufacturing and in services, could help make a company quite, what would I say? Could really help to improve the performance of a company as it pertains to quality. And quality is very important as part of strategy and as part of making an organization meet its mission and its vision and meeting customer expectations.